Welcome everybody to our multi-institutional AGN seminar series, and welcome back if you've been part of this series before, and if you haven't, I just wanted to give a little bit of background. We started this seminar series during the peak of the pandemic. We were all in lockdown, and a bunch of us had gotten together to discuss sort of brainstorming ideas surrounding the topic of adaptive optics and what science can be enabled in the field of AGNs. And this was really motivated by a mission concept study called ORCUS, which is a laser beacon concept to enable diffraction limited performance all the way into the optical with very high sensitivity on 10-meter class telescopes and beyond. And after a series of these really motivating discussions, Gabby and I, Gabby Canaliso, who is here as well today, decided to have a very focused seminar series centered on the AGNs. And it was, the thought was to have it be a little bit more informal and focused with experts in the field, where we can have, some informal questions, brainstorming sessions, and maybe forge some collaborations, which some of us have already done so far. So it's been really a lot of fun. And so from really popular demand, we decided to continue it for the semester. And I'm delighted that we got Jonelle to give the first talk in the semester. She is really an expert in adaptive optics observations and dynamical studies of supermassive black hole measurements and nearby galaxies, and really understanding all of the subtleties that go into gas and stellar kinematics, and all of the different methods in which black hole masses are measured, and of course, understanding black hole galaxy scaling relations and supermassive black hole and galaxy coevolution. And I wanted to just give you a little bit of background. Jonelle got her PhD from UC Irvine. She then went on to get an NSF postdoctoral fellowship at UT Austin. And that was followed by a Mitchell postdoc fellowship position at Texas A&M, where she stayed on to be an assistant professor at Texas A&M. So I wanted to say that Jonelle is leading an amazing array of cutting-edge observations using state-of-the-art facilities, both on the ground and space. I was really amazed. These programs range from Gemini, where she has a long-term project, Keck, ALMA, HST, and she was recently awarded a highly competitive Cycle 1 JWST program. So I had asked Jonelle before if she would be able to give a talk, and I'm delighted that she was able to start our seminar series this fall. And so that I would like to welcome Jonelle, and I'll hand it over to you. Thanks so much for coming.
Awesome. Yeah, thank you. Thank you for that really nice introduction. Yeah, so I'm going to be talking about dynamical measurements of supermassive black holes in nearby galaxies and a few projects that will help us learn about how black holes and galaxies co-evolve. So supermassive black holes reside at the centers of essentially every massive galaxy, and we have strong pieces of evidence for the presence of black holes. Of course, that includes an impressive image of a black hole shadow in M87. The best dynamical evidence we have, though, comes from our own galaxy, where we can track the paths of individual stars as they orbit close to the black hole. Beyond the Milky Way, though, black holes have been dynamically detected in about 100 galaxies to date. So there are three main ways to dynamically detect black holes, and they involve modeling the observed kinematics of stars, gas disks, and water maser disks. So stellar-dynamical modeling is the most widely used method, since the motions of stars always reflect the underlying gravitational potential. However, extracting a secure black hole mass measurement from the observed kinematics can be challenging just due to the complexity of the models, which are also computationally expensive to calculate. Also, the models can be subject to a number of systematic effects, such as mass degeneracies between the black hole, stars, and dark matter, as well as the systematics that are associated with making assumptions about the intrinsic shape of the galaxy, like whether it's axisymmetric or triaxial. In contrast, gas dynamical modeling is conceptually simple, but the drawback of this technique is that gas can be influenced by non-gravitational forces. And so the main assumption, which is often circular rotation, needs to be verified. Furthermore, many of the observed, at least ionized gas disks, exhibit velocity dispersions in excess of what you would expect from just bulk rotational motion alone. And the physical origin of that intrinsic velocity dispersion is not known, but it could be dynamically important. And if so, it should somehow be included in the modeling to prevent a biased black hole mass measurement. And then in a few cases, black hole masses have been measured using megamaser disks in active galaxies. So this technique provides strong black hole mass constraints as the sub-parsec scale circumnuclear disks are observed deep within the black hole's gravitational potential. Unfortunately, such disks are rare and they require special physical conditions and nearly edge-on inclinations to produce the maser amplification. There can also be departures from Keplerian rotation because of significant gravitational contributions from the disks themselves. So dynamically detecting black holes requires high angular resolution observations that probe the innermost regions of galaxies where the gravitational potential from the black hole dominates. So that region is the black hole sphere of influence. So the black hole sphere of influence is small for a typical supermassive black hole with a mass of about 10 to the 8 solar masses. The black hole sphere of influence is roughly tens of parsecs. Therefore, resolving such small scales with the current observational facilities limits our measurement of black holes to those that are nearby, so roughly within 100 megaparsecs. The Hubble Space Telescope, with its great angular resolution, has therefore played a fundamental role in detecting black holes over the past 25 years. From those high angular resolution observations, we find that the masses of black holes correlate with the large-scale properties of the host galaxy. There have been numerous relations that have been found over the years. So here are two of the more well-studied relations between the black hole mass and stellar velocity dispersion, or m sigma, and then the black hole mass and bulge luminosity, or ml. So these relationships suggest that somehow black holes and galaxies co-evolve. However, the details are very poorly understood. So a cosmic census of black holes has important implications for galaxy evolution, but currently the local black hole mass census is highly incomplete. So this is particularly true for low mass black holes below about a few times 10 to the 7 solar masses, and high mass black holes above about a few times 10 to the 9 solar masses. So this leaves major questions regarding the distribution of black hole masses with host galaxy properties. With the present measurements, the slope, intrinsic scatter, and even the shape of the correlations for low and high mass black holes are not well established. For example, recent progress detecting high mass black holes in brightest cluster galaxies hint that these objects could lie above m sigma, but there's still too few available measurements to firmly characterize the relations at the high mass end. The uncertainties are equally severe at the other end, the opposite end, where spiral galaxies with low mass black holes appear to exhibit large scatter below both the m sigma and the ml relations. And new measurements in low mass early type galaxies also show signs of deviations below the relations. Another issue is that dynamical black hole mass measurements have been made in galaxies that are not representative of the local galaxy population. So here I'm showing a plot of galaxy K-band luminosity and size, so effective radius. The green points on here are galaxies with current dynamical black hole mass measurements. And for comparison, the gray contours illustrate the nearby galaxy population from Sloan. So as you can see here, the black hole mass measurements have been made in a biased set of galaxies. So at a given luminosity, galaxies with small sizes relative to the nearby galaxy population have been preferentially targeted. However, proper sampling of this luminosity, or equivalently mass size parameter space, is really important. So as you move in this direction, a number of galaxy properties change, such as stellar velocity dispersions, mass to light ratios, bulge fractions, gas content, stellar populations, and morphology. Also, galaxies that grow in different ways end up on different regions of this plot. So clearly, we need to do a better job of sampling this parameter space in order to obtain a more complete census of local black holes in a wider range of galaxies that have experienced diverse evolutionary histories. Okay, so there's obviously still a lot left to be learned about how black holes and galaxies are connected. And as I just described, the local black hole mass census is incomplete, and we still don't have a good understanding of the primary physical mechanisms that drive the empirical relations between black holes and galaxies. So we therefore need more precise black hole mass measurements, again, particularly at the extremes of the black hole mass scale and over a wider range of galaxies that have grown in different ways. And we need to better quantify the intrinsic scatter and the magnitude and distribution of the intrinsic scatter of the scaling relations. In addition to that, other fundamental questions remain unanswered. So just as a few examples, do black holes and galaxies grow in symbiosis with each other over time? Or does the growth of the black hole precede that of the host galaxy or vice versa? Are there black holes in low mass galaxies with masses less than the Milky Way and in globular clusters? How do supermassive black holes form? What are their initial seed masses and how can they acquire so much mass so quickly in the early universe? So yeah, with the rest of the talk, I'm just going to highlight some recent observational and modeling advances and several projects I'm involved with that have at least allowed us to start to address a few of these questions. So yeah, HST has played an important role in detecting black holes over the past 2 decades. More recently though, significant progress has been made using adaptive optics, AO, on large ground-based telescopes. So AO can deliver similar angular resolutions as HST, but has the added advantage of being used with larger telescopes, and it operates in the near infrared. So galaxies that were previously pretty tough to observe with HST because they were too faint or perhaps a little too dusty can instead be studied in great detail with AO on large telescopes. So as a result, AO has contributed some of the most massive and least massive black hole mass measurements ever made and everything in between. So this includes studies of giant elliptical galaxies with several billion solar mass black holes to low mass early type galaxies with sub-million solar mass black holes. Given the extensive observational and modeling effort involved in just a single determination, the approach that has been used for years is to measure one or a few black holes at a time. But advancing the field also requires examining large homogeneous data sets of carefully selected samples. So one such survey was conducted with AO-assisted Symphony on the VLT. They're producing 25 dynamical black hole masses with galaxies selected to explore these poorly populated regimes of the black hole scaling relations. So that includes high velocity dispersion, early type galaxies, low velocity dispersion, and pseudobulge galaxies, and merger remnants. So we're also carrying out a large black hole program at Gemini North. So we've been allocated 253 hours over the next few years to measure black hole masses through stellar dynamical modeling methods in 31 galaxies using the integral field spectrograph NIFS assisted by AO. So earlier I showed this plot and highlighted how the current dynamical black hole mass measurements, so in green, have been made for galaxies that are not representative of the local galaxy population. And so our program is aimed at addressing this troublesome bias. So here in red are galaxies in our sample. So the red numbers correspond to those images that you're seeing around the plot. The red crosses are also in our sample. There's just no image that's being shown. So our sample significantly increases coverage of this important parameter space without sampling the already well-populated region within that dotted oval. The galaxies in our sample span a wide range of properties by design. For example, the stellar velocity dispersions range from 60 to 300 kilometers per second. Also, our sample contains a number of spiral galaxies. We'll nearly double the number of black hole mass measurements made in spiral galaxies, therefore exploring a regime that largely hasn't been tackled with stellar dynamical modeling techniques. So far, we've acquired NIFS observations for 12 galaxies, so that's fully complete. The 12 galaxies already enhance the diversity of black hole hosts, and we've observed the most luminous, largest galaxy in the sample, as well as low luminosity galaxies with different effective radii. And so here are just some example spectra. So extracted at the nucleus and then about an arc second away for the most recent 6 galaxies we finished observing. And the data quality here really are excellent. So from those absorption lines, we measure the velocity distribution of stars along our line of sight. And we characterize that distribution by its center, the velocity, the spread, the velocity dispersion, and then asymmetric and symmetric deviations from a Gaussian. So that would be H3 and H4. In other words, the skewness and kurtosis. So we measure this distribution as a function of spatial location, and that's what you're seeing here for 2 galaxies in the sample. So this is the velocity map, and you can see both of these galaxies are rotating. This is the velocity dispersion map, and both of these galaxies show central velocity dispersion peaks. In the case of this galaxy, the stellar velocity dispersion reaches 370 kilometers per second, right at the nucleus, whereas this other galaxy, NGC 1022, shows a peak at 60 kilometers per second. So again, you can see here that we really do have a wide range of galaxies in our sample. We've also found some interesting cases. So this is a rotating edge-on early type galaxy where there's a decrease in the velocity dispersion at the center. So the sigma drop could imply a non-detection of a black hole, which would still be interesting because that would mean this galaxy lies well below both the current M sigma and ML relations. But the sigma drop could also result from a distinct dynamically cold component of stars at the nucleus. And dynamical models will be able to provide more information and be able to distinguish between those scenarios. Besides the AO observations, we have HST images for the entire sample of 31 galaxies in 3 filters with C3. We also have the entire sample now observed with the integral field unit LRS2 on the Hobby-Eberly telescope, and even wider field IFUs, Virus P and Virus W, on the 2.7 meter telescope at McDonald Observatory. So we're constructing these orbit-based stellar dynamical models. So the main idea is that the galaxy's gravitational potential consists of contributions from the black hole, stars, and dark matter. The stellar potential is determined from the HST image, deprojecting it for a given viewing orientation and multiplying by a stellar mass to light ratio. Then we generate a representative orbit library, and the orbits are integrated in that potential. We assign weights to the orbits such that the superposition best reproduces the observed kinematics from the spectroscopy and the brightness from the image. And then many models are calculated with different values for the parameters of interest, like the black hole mass, and the best model is taken to be the one that most closely matches the data. So this plot here summarizes the modeling results for that first galaxy that I showed, PGC 12557. So these are contours of chi-squared as a function of black hole mass and H-band mass to light ratio after marginalizing over the other 3 parameters. So at each gray point, a model was calculated, and then that red point denotes the best fit model, and the 1 sigma contour is shown by that thick red contour. So ultimately, we're finding a black hole mass of 2.3 times 10 to the 9 solar masses. And then over here is a comparison between the observed NIFs and LRS2 data, and then the best fit model in green. So we actually used 4 independent orbit-based modeling codes that our team has access to, each of which follow the same general approach, but the implementation is different. And we're recovering consistent black hole masses, so that is very reassuring, and it allows to get us a handle on the uncertainties too. Okay, so PGC 12557 hosts a high mass black hole. With our black hole mass, the galaxy is consistent with M sigma, but clearly lies above ML, even when conservatively using the galaxy's total luminosity. So it actually turns out that this galaxy looks similar to other local galaxies that are also positive outliers from ML. So those are shown in red up here. So all of these galaxies are early type galaxies and are compact. So they have small sizes of 1 to 3 kiloparsecs for their K-band luminosities of about 10 to the 11 solar luminosities. So that corresponds to stellar masses of about 10 to the 11 solar masses. And they have large central stellar velocity dispersions. So these nearby compact galaxies host some very massive black holes, but they're very different from the kinds of galaxies you would actually expect to find at the upper end of the black hole scaling relations. So as an example, here I'm showing an optical image of some of the galaxies in the Perseus cluster. So NGC 1275 is the brightest galaxy of the cluster, and it's the kind of galaxy you would expect to find at the upper end of the black hole scaling relations. So these kind of galaxies are large elliptical galaxies, typically with effective radii of like 10 kiloparsecs. And they're often dispersion-supported galaxies showing little to no rotation. In contrast, NGC 1277, located nearby, is one of the compact galaxies. So NGC 1277 is small and flattened and rapidly rotating, and that's in sharp contrast to NGC 1275. Instead, the nearby compact galaxies like NGC 1277 and also like PGC 12557 that I was describing earlier, they look quite similar to the typical quiescent galaxies at a redshift of 2, so the so-called red nuggets at a redshift of 2. Since the local compact galaxies look very similar to the redshift 2 red nuggets, they could be relics. So the redshift 2 red nuggets grow in size and a little bit in mass through a series of mergers to produce the massive early type galaxies of today. Instead, the sample of nearby compact galaxies may have taken a different growth pathway. So they may have experienced a more passive evolution, one in which they didn't undergo the same amount of mergers to build up the outskirts of their galaxies. If true, then the nearby compact galaxies like PGC 12557 and NGC 1277 could reflect a previous time when the local ML relation did not apply. Galaxies contained overmassive black holes, and it was the growth of the host galaxy that needed to still catch up. In other words, these overmassive black holes could suggest that black hole growth precedes that of the host galaxy. I should also mention another explanation for these overmassive black holes. So another possibility is that we simply don't have enough measurements at the upper end of the black hole host galaxy relations. So neither the form of the relations nor the intrinsic scatter is well determined in this high mass regime. Therefore, the compact galaxies could just lie in the tails of a distribution between black hole masses and galaxy properties that have yet to be fully established. Okay, so that was an example of a stellar dynamical black hole mass measurement from the Gemini Large Program. And while the Gemini Large Program is focused on those kind of measurements, several of the galaxies in our sample also exhibit prominent near-infrared emission lines in the NIST data. So one such case is NGC 4111, which I also briefly mentioned before. So NGC 4111 is that nearby S0 edge-on galaxy. It actually has this dusty polar ring. So this is visible in the HST imaging. So it has an extent of about 6 arcseconds or 450 parsecs. And the NIST field of view is 3 arcseconds by 3 arcseconds. And we're finding warm molecular gas, so H2, immersed in the dusty polar ring. There was also previously published Stellar and O3 gas kinematics for this galaxy from Suron through the Atlas 3D survey. So while the NIST data are focused on the inner regions, so within about 100 parsecs, the Suron data cover larger spatial scales within about 1.5 kiloparsecs. And the ionized gas, the O3, is present in both the polar ring and the galaxy disk structures. So again, the small scale NIST stellar kinematics show that the galaxy is rotating and that the velocity dispersion from the stars drops at the center. And then we have the large scale Suron stellar kinematics, and they show similar features. So the kinematic position angle from Suron and NIFS agree with each other, and they also agree with the photometric position angle from the HST image. However, the H2 velocity field measured from the NIFS data counter-rotates with respect to the stars. So this is a map of the H2 gas distribution, which shows that the gas distribution is brightest toward the northwest, which if we take to be the near side of the distribution, we see that is red shifted, whereas the far side is blue shifted. So that suggests an inflow of gas. In contrast, the ionized gas from Suron shows something different. So that's shown over here. This is the O3 velocity fields. There's a slight kinematic twist, and the global position angle doesn't coincide with any of the principal axes of NGC 4111. So not with the photometric position angle or the kinematic position angle from the stars. So this emission line gas is in this unstable configuration. So we examined the O3 velocity field from Suron more closely and applied kinemetry to the ionized gas velocity field. So that's what's shown here again. We used the best fitting ellipses from the kinemetry analysis of the Suron stellar field. So the resulting model here gives the component of the gas in circular rotation in the galaxy's equatorial plane. So by subtracting this model from the observed velocity field, we obtain the gas component that's not within the equatorial plane. So we call that a polar component, since it's aligned with the minor axis of the galaxy and the observed dusty polar ring. Next, we ran kinematry on this polar gas velocity field and acquired the ordered motions. So this is a model that represents the part of the ionized gas that's in circular orbits in the dusty polar ring. So ultimately, we find that this Scellar ionized gas velocity field is actually the superposition of two components. So we have one rotating in the main galaxy plane and then one that's rotating in the dusty polar ring. Also, by subtracting these maps here, we obtain the non-circular motions in the polar ring. So that's what's being shown over here. So this resulting residual map seems to possibly display kind of a spiral-like pattern, which also might hint at inflowing gas. Although the angular resolution of the Scellar data is much worse than the NIFS data, when looking at these residuals within the NIFS field of view here, there could be hints of redshifts toward the northwest and blue shifts toward the southeast, possibly indicating a connection with the NIFS H2 velocity field, which also shows that same redshift and blue shift structure. So with that analysis, we're thinking that this dusty polar ring originates from the capture of a dwarf galaxy by NGC 4111, given an estimated gas mass of about 10 to the 7 solar masses. The ionized gas from Scellar is composed of two kinematic components, one that's rotating in the galaxy plane and then one with orbital motion in the polar ring. And then the residual non-circular motion in the polar ring has a spiral-like structure that connects with the small-scale warm molecular gas. So the NIFS H2 kinematics suggest inward motion with the near side of the gas distribution being redshifted and then the far side being blue shifted. Some of this inflowing gas may be settling into the galaxy plane and forming new stars, which could cause the observed stellar velocity dispersion drop at the center of the NIFS and the Scellar data. At least some of the inflowing gas seems to be reaching the nucleus, though, triggering a low luminosity AGN. So yeah, our program is focused on stellar dynamical black hole mass measurements, but the high quality NIFS data also allows for these kind of detailed studies of emission lines and potentially studying black hole feeding. Okay, so AO on large telescopes has made stellar dynamical black hole mass measurements more routine. In addition to AO on large telescopes, we now have these very sensitive wide field IFUs like MUSE on the VLT and KCWI on KEC. So these instruments provide a very efficient way to hunt for extremely high mass black holes. Such high mass black holes are difficult to detect because they're rare, so you have to search for them over larger distances, and because they're expected to be found in high mass galaxies, which often have surface brightness cores. So lower mass elliptical galaxies tend to have rising light profiles toward the nucleus, like you're seeing here with the gray lines, whereas the very massive ellipticals tend to have a deficit of stars in the central region. It's actually quite challenging to obtain the high signal to noise observations needed to reliably measure the stellar kinematics in these faint galaxy centers. So the central cores of massive elliptical galaxies are thought to result from the gravitational scouring of binary black holes, where stars passing close to the binary can get scattered out to larger radii. So as a result, you might expect to see a correlation between the core size and the black hole mass. And recent studies have started to see possibly such a relation. We're targeting giant elliptical galaxies with very large diffuse cores using the integral field spectrograph KCWI on KEC. So we have observations of 4 galaxies with core sizes of 1.5 to 4.5 kiloparsecs. So the galaxies could harbor black holes with masses larger than 10 to the 10 solar masses. To date, there have only been 2 black holes with such large masses. So with KCWI, we're able to obtain high quality spectra in a reasonable amount of time, despite these very faint galaxy cores, which are much fainter than other massive galaxies that have been studied before. So with about 3 hours on source for each of the 4 galaxies, we have high signal to noise spectra over a 8 by 15 arcsecond fields. So these are just some example spectra. So at the nucleus and then a little bit further away for one of the galaxies. And then these are maps for 2 galaxies, both the velocity and velocity dispersion. So both galaxies show very low amplitude rotation, and there's a rise in the velocity dispersion at the center. So these observations were done with the small slicer of KCWI to focus on the inner portion of the galaxy. We also got large slicer observations with KCWI with multiple pointings to cover even larger scales for all of these galaxies. And so that's what you're seeing here. So that white cutout at the center actually shows the coverage from the small slicer data. So the top and bottom portions of this velocity map show intriguing signs of a plus and minus 40 kilometers per second rotation along a kinematic axis that is misaligned relative to the photometric major axis, which is shown here in black. So there's a misalignment of about 30 degrees. So kinematic misalignment is a strong indicator that the galaxy is triaxial in shape. So we also recently went back and got additional pointings that are shown by those red boxes needed to better quantify the extent and amount of rotation. So we're working on constructing fully general triaxial stellar dynamical models that fit to this data, and we'll be able to pin down the very likely high mass black hole here. So that work is still ongoing, but I wanted to show you an example of a completed analysis. This was done by another group. So this is Home 15A. It's the brightest cluster galaxy of Abell 85. And this was observed with MUSE. So again, this galaxy has this very faint diffuse stellar core here. So the core is about 2 magnitudes fainter than the depleted cores of other massive early type galaxies. Despite this faint core with just 1 hour on source, they got high signal to noise spectra over this 1 by 1 arc minute field. And using axisymmetric stellar dynamical models, they found a black hole mass of 4 times 10 to the 10 solar mass black hole. So this is the largest black hole detected to date. So the stellar dynamical modeling technique also, besides giving you black hole masses, is useful for studying the galaxy's orbital distribution, testing core formation scenarios, and inferring galaxy assembly histories. So besides those observational improvements with AO and these highly sensitive wide field IFUs, there have been efforts to improve the stellar dynamical models as well. So a couple of triaxial codes have recently been developed. Almost all the stellar dynamical black hole masses so far have been made assuming axisymmetry, but being able to explore triaxiality is important for modeling the most massive galaxies, as we're starting to see with some of those KCWI observations, and for modeling features like bars. So going forward, the triaxial codes will have an important impact on both the upper and lower ends of the black hole host galaxy relations. In addition, there have been improvements made to existing codes, such as speeding them up and updating orbital libraries. And there's been work to constrain models, not just with the observed kinematics, but also incorporating stellar population information like ages and metallicities. Okay, so let me switch over to gas dynamical black hole mass measurements. So up until a few years ago, almost all the black hole mass measurements have been made from rotating nuclear gas disks from HST observations of ionized gas. But the molecular gas from radio observations now offers an attractive alternative. So the dynamical modeling assumes that gas participates in circular rotation in a thin disk, and the cold, dense molecular gas is likely to have a much smaller turbulent motion compared to the warmer ionized gas disks. So one of the major systematics associated with gas dynamical modeling could be much less of a concern with radio observations. Also, the data cubes that you get from radio observations provide more complete coverage of the disks compared to just, say, the handful of spectra that you get from a few HST apertures. So this means that tighter constraints can be placed on parameters like the disk position angle and the inclination angle, which have an impact on the inferred black hole mass. So the first ever black hole mass measurement made from CO emission was done several years ago using the radio facility KARMA. The black hole sphere of influence was barely resolved, even though this galaxy is very nearby, and the observation required tens of hours to complete. Nevertheless, it opened up a new way to measure black hole masses. Since then, ALMA has provided this huge step up in terms of sensitivity and angular resolution compared to the previous radio facilities. So we're now able to more routinely map gas kinematics within the black hole sphere of influence of many galaxies, and we're able to achieve the precision black hole mass measurements necessary to really advance the field. There's been an uptick in the number of ALMA-based black hole masses in the last couple of years, And now the number of molecular gas dynamical masses is about equal to the ionized gas dynamical masses. So with ALMA, both the low and high mass black holes can be probed, and we can sample across the Hubble sequence. So I've been part of a collaboration using ALMA to carry out black hole mass measurements in this way. We're obtaining ALMA observations of early type galaxies at the upper end of the black hole relations that host regular dust disks in HST images. So such dust morphology suggests the presence of cleanly rotating molecular gas. Our ALMA programs, combined with similar data in the archive, show that there are a number of promising targets for molecular gas dynamical modeling. And so here are some examples. So these are maps of the CO flux distribution, and then these are maps of the radial velocity. So you can see that there is fairly regular disk rotation. So this highlights the opportunity afforded by ALMA to take an accurate census of black holes. So this is just a really beautiful measurement that I think showcases ALMA's potential. So NGC 3258 is a nearby elliptical galaxy. With brief cycle 2 ALMA observations at 0.4 arcsecond resolution, we saw this central high velocity emission, but these Keplerian upturns here are not that well resolved. So we went back in cycle 4 and got 0.1 arcsecond resolution ALMA observations. And this is what the position velocity diagram looks like along the major axis. So the data highly resolve the central gas kinematics, and these Keplerian upturns are just really, really clear. So we fit rotating disk models that allow for a slight warp in the disk to these cycle 4 observations. And then this is a comparison between the observed velocity map and the best fit model velocity map. So we find a high mass black hole with a mass of 2.2 times 10 to the 9 solar masses with a statistical uncertainty of just 0.2%, an estimated systematic uncertainty of about 0.6%, and then a 12% uncertainty due to the distance. So the cycle 4 data fully resolve the black hole sphere of influence, which is 0.9 arcseconds. So this is the most precise black hole mass measurement to date for any early type galaxy and rivals some of the maser black hole mass measurements in spiral galaxies. So earlier I discussed a sample of nearby compact galaxies that resemble the redshift 2 red nuggets that contain overmassive black holes relative to the ML relation. Besides determining stellar dynamical masses for the black holes in those nearby compact galaxies, we're also pursuing molecular gas dynamical black hole mass measurements. So we've identified 8 nearby compact galaxies that have well-defined nuclear dust disks in HST I-band images, so that's what's being shown here. With the exception of one galaxy, none of the other galaxies have been previously targeted with any millimeter or submillimeter facility. And so the brightness of the CO emission, like right at the nucleus, is not known. Therefore, we obtained brief ALMA observations for 3 of the compact galaxies at somewhat moderate angular resolution, so about 0.2 arcseconds, which would just resolve the expected black hole sphere of influence. We wanted to first test for the presence of CO on these small scales, and then if successful, later we can go back and obtain higher resolution observations that really resolve the black hole sphere of influence and really pin down the black hole mass if needed. So from the ALMA observations, we indeed found nice CO disks in regular rotation for all 3 of the galaxies, and we completed fitting dynamical models to the spatially resolved kinematics for one galaxy, this one here, UGC 2698. So for our gas dynamical models, we assume that the gas rotates in a thin disk. At each radius in the disk, we determine the circular velocity relative to the systemic velocity based on the enclosed mass, which depends on the black hole mass and the extended stellar mass distribution. The model velocity field is generated on a subsampled pixel grid and is projected onto the plane of the sky for a given value of inclination. The intrinsic line of sight velocity profiles are taken to be Gaussian and are centered on the projected line of sight velocity at each point on the model grid, and they're given an intrinsic width. After rebinning back to the native pixel scale, we account for beam smearing and we directly compare the model cube to the observed data cube. And then we just look for the best combination of parameters. So when we do this for UGC 2698, we find a black hole mass of 2.46 times 10 to the 9 solar masses. And so just over here is the comparison between the observed flux, velocity, and velocity dispersion, and then our best fit model. So it turns out that UGC 2698 is consistent with both the M sigma and ML relations. So this is in contrast to the Stellar-Dynamical black hole mass measurements made in 4 other compact galaxies that you're now seeing in red here. So UGC 2698 is the largest compact galaxy in the sample in terms of its effective radius and its mass. So it is still possible that the nearby compact galaxies are analogs of the redshift 2 red nuggets and suggests that black holes at a redshift of 2 were overmassive relative to their host galaxies. In that case, though, the other compact galaxies, like NGC 1277, may represent more pristine relics of the redshift 2 red nuggets, whereas UGC 2698 may represent an intermediate stage. So UGC 2698 may have undergone some mergers to bring the galaxy more in line with the local black hole scaling relations. Or, like I said before, there could just be more scatter than we currently think in these relations at the upper end. In order to gain a better understanding, we need more black hole mass measurements at the upper end of the black hole mass distribution and to apply independent black hole mass measurement methods to the same galaxy. So the stellar and gas dynamical black hole mass measurement methods suffer from several but different systematic effects. And direct comparison between the methods has only been done on a few galaxies with mixed results. So more studies are needed in order to draw conclusions regarding the consistency of the 2 methods, the subsequent effects on the black hole scaling relations, and to determine the intrinsic scatter of these relations. So I don't know if I should skip over this because I know we're kind of running a little bit long here. So if people want to ask me about M87 and our JUST program that we have to study M87, I'm happy to do that. So let me just go ahead and put up this summary slide here. So just again here, the local black hole mass census is incomplete and we don't have a good understanding of the primary mechanisms that are driving the black hole galaxy scaling relations. So we do need more measurements at the extremes of the black hole mass scale and over a wider range of galaxies that have grown in different ways. And we need to better quantify the intrinsic scatter in the relations. So recent progress has been made using AO on large ground-based telescopes, new wide field sensitive IFUs, ALMA, as well as updates to the modeling methods. And then in the near future, JUST will certainly contribute as well. So yeah, I'll stop there and take questions. Thanks.
So let's thank Jonelle. We have our reaction here. So thank you so much, Jonelle, for that wonderful talk, and we'll take questions. So I think Claire has a question. Oh, Claire, can you unmute yourself?
Yeah, I have a question about a slide that I didn't catch the number on, but it's the one which says molecular gas dynamical modeling, Cohn et al. 2021.
Oh, sure, like the method.
Keep going. It has some spectra on the right.
This one?
Yes. So at least with, no, yeah, that one. At least with the Euler mergers that we took a look at, there seems to be some of them that have a high molecular gas mass in the very central portions that actually can play a gravitational role and have an influence on what you conclude is the mass of the black hole as opposed to the mass of the central jump in gas density. So I wondered, it seemed like you ought to be able to get at that with this method, but I didn't see it listed on here.
Yeah, no, that's a good point. So the method that I listed here is kind of like our baseline fiducial model, but we definitely did explore accounting for the gas mass. And now off the top of my head, I don't remember how much it is. It's in the paper. This is actually published now. But we did run a model where we did include the gas mass and it didn't make an appreciable impact on the black hole mass. So yeah, we explored various, things that we changed a bunch of things within the model and our assumptions and built that into the error budget as well. So that's what the error bars on that I quoted here also reflects our various possible systematics.
Because it's, from a physics point of view, it's interesting that if there is a significant gas mass right in the center. So it's good to
Right.
No one
Yeah.
epoch counts.
I wish I remembered the number. It definitely was not large, but we did try to include it in the modeling anyway.
Thank you.
Jim?
Yeah, how many supermassive black holes would you say we have very precise masses of? I've been thinking that's many tens. What's your subjective feel?
Yeah, that's a really good question. So, I mean, the most precise masses definitely come from the megamaser measurements, which I didn't talk about at all.
They're much better than reverberation mapping ones.
Well, so I'm counting reverberation mapping as like a separate bin, since it's not a dynamical measurement, and you do need to calibrate to the local like relation. So you get something that's proportional to the mass, and then you have that F factor to actually convert it to a mass. So like
you're not counting that as a dynamical?
Yeah, I'm not counting that as a dynamical measurement. Yeah. But yeah, I mean, to answer your original question, I mean, maybe tens. I would have to think a little bit harder about that, but I do think
I realize that's a subjective question. I'm asking.
Yeah, it's very a subjective question. Yeah.
Then for the rest of them, if I get a mass within a factor of 2, would you give me a good grade on that, or should we really be able to do much better than that?
I mean, I feel like
answer.
I feel like we should be able to do better than that. I mean, we worry. I mean, I breezed over M87, but M87 is this example where we have so many black hole mass measurements, over the past 40 years from both stellar and gas dynamical measurements, and also, I mean, I can put this up. Also, of course, the EHT measurement, as well as a third independent measurement. And here we are worrying about a factor or 2. So the stellar and gas dynamical black hole masses over the years, even though the data has improved, the modeling methods have improved, we continue to have this factor of 2 disagreement between the stellar and gas measurements. So there's definitely room for improvement on both sides. And that's kind of, we thought this was a good thing to do with JWST, just because like there are all these built-in assumptions, and JWST can help with the data on the data side of things too. But yeah, I think we should be able to do better than a factor or 2, although it's not uncommon to see a factor or 2 difference between the methods.
Okay, thank you.
Thanks, Jim. Matt?
Jonelle, great stuff. Love it, of course. You had a beautiful montage slide that showed all of these velocity fields and then direct images of a bunch of gas measurement galaxies. And one thing struck me about that was amazing. So here's my concern about this. At this resolution, there are, of course, a lot of rather beautiful classic rotating disk maps there at this resolution. Now, but there's quite a few of them where there's more stuff going on. Now, if I only wanted to do gas measurements of the black hole, suppose I just didn't want to know anything else. I'm not saying that's good science, but don't tell me anything more. I'm a little bit nervous. There's so much more information. There's so much more going on. Let me give you a few examples here, because you see a lot of these things have twists or sometimes S distortions and so on. Now, you mentioned a few explanations of that. You can have a polar ring, from some accretion event, which is counter rotating, and you combine those two things in O3, and that makes a complicated velocity field. You could have, maybe as a result of that, you have a cold disk, which is settled down at some angle in there. That complicates things. I suppose you could have biconical outflows of some things. Maybe you mentioned definitely a factor here is triaxiality. That's a serious problem in some things. Let's see, I haven't got all of the, and then of course, some people consider that some of these distortions comes from maybe some kind of bar in the gravitational field, which might actually cause inflow to happen. And you might be seeing this in some of your data. That's very interesting too. So all these things are fascinating, but what if you're just, no, I just want to know the black hole mass. Don't give me all these complications. But I'm thinking, man, I mean, it seems like, what if half of the galaxies has a complication in it? Because the galaxies that are doing all these things, then I'm wondering if we're going to be able to just, no, I just want to know the black hole mass. Just give me an industrial production, of a lot of black hole masses. So anyway, just a thing in the back of my mind when I see such beautiful data.
Yeah, I mean, you're absolutely right. So now that we are, getting better data, the models need to then be updated because you start to see these complications. I mean, not that they weren't there before, not that maybe the black hole masses weren't biased before with the worst data. But yeah, I mean, we definitely have been working on improving that like simplified, flat disk rotation because that is a simplified model. So we can do things
warps.
like
you
warps,
got
right?
warps
So
in there.
we absolutely have been running. I mean, if the data justifies it, running a warp disk model where the PA and the inclination of like various rings can change with radius. We also have been trying to explore like, what if there's sub-Keplerian rotation? There's not a real great way to do that without getting into like all sorts of like hardcore, like, like physics in there. So it's definitely something where we can see what happens if we put some kind of like parameter into our model that allows for sub-Keplerian rotation and see how that impacts the black hole mass. But yeah, I mean, you're absolutely right that, with this great data, there are more things that are popping out. And so that in some cases does justify the need for more complex models. Yeah. But so but I will say that if you can find a case that is, it's not obvious complications, it does look like this nice disk that is circularly rotating, the simpler method is what you want. And I would put a lot more faith in something like that as opposed to, I mean, so obviously I do both stellar and gas dynamical modeling. And obviously I have opinions about both sides, but definitely with the stellar dynamical modeling, a lot of systematics and a lot of things can get hidden in the very complex modeling that happens. So you might not realize that something is happening and it's hard to kind of extract, what is really going wrong. So if you do have a great case of simple flat disk rotation, then, the simpler method is the way to go there. There's less systematics that can be hidden in there. But you do have to find those cases. So,
So I think Gabby, we'll take Gabby as the last question, and then Jonelle, if you can stay a little bit later, maybe I'll ask one question at the end. So Gabby.
Yeah, so great talk, really incredible data. And my question is somewhat related to Matt's, but I'm thinking about the stellar kinematics. And it's so reassuring because that their motions are dominated by gravity and et cetera, et cetera. So you have wonderful wavelength coverage and you don't have to worry about using lines that may be interstellar. So, but my question is, how often, or have you looked at it, how often do you see a different kinematic component that comes from interstellar, like calcium lines or sodium line, which sometimes you see outflows? How often do you see this?
Yeah, so usually when those kind of lines, like say, this is probably more applicable to, not like say AO data with a small wavelength like near infrared coverage that's focused on say the K-band, CO band heads, but like with wider field optical observations with wider wavelength coverage. So usually people fit just like everything that's in there. So it's all the lines together. I don't know of anyone that has say focused on an interstellar line and only looked at the kinematics from that. I mean, I very well could be missing something, but yeah, no, that would be interesting to see. I mean, people usually just fit all the lines that are there at once instead of focusing in on a particular line to do that.
So my question is for two reasons. I mean, on the one hand, because it would be kind of interesting to double dip, right, and use this data to look for inflows or outflows or kinematically detached gas or what have you. But the other reason is sometimes, in different things like looking at stellar populations or sometimes you're stuck with a line, right? I mean, depending on what kind of data you have, and you might have to work with things that are contaminated by interstellar lines. So I'm just wondering how much of a concern it is. So on the one hand, very cool. On the other hand, how concerning is it?
Yeah, I mean, yeah. So I mean, yeah, I guess I don't have a good good answer. I mean, I think it's something I have not personally thought about, but I think it's a good question. Yeah.
Thank you.